We want to move on now to our next topic, which will be examining the electrical motor diagnostics. Integrated motion control systems contain match components such as motors, motor drives, controllers, and encoders. The motor tests used to measure and evaluate various electrical characteristics and performance parameters of motors are therefore critical tools that can help monitor overall motion system performance. Selecting the right tools is also critical. Motor test equipment can be either offline with no power supplied to the motor or online where power is applied and the motor is running. Motors can be tested either standalone on a test bench or in situ where installed in the equipment they power. The test equipment itself uses internal voltmeters, ammeters, and ohm meters to measure and calculate a motor's various performance parameters. Recommended tests include stator winding resistive imbalance testing, stator winding insulation resistance testing, polarization index testing, step voltage testing, and surge testing. Needless to say, there are many types of motor test equipment, including online and offline, single-phase and three-phase, portable and benchtop, plus rack-mount motor test equipment. Our next speaker will help us sort out and better understand how electrical motor diagnostics help ensure optimum motion system performance. He'll show us common as well as advanced static and dynamic tests available for motor system evaluation with specific attention given to their capabilities and limitations. Please join me in welcoming our next speaker, Howard Penrose, the Vice President of Engineering and Reliability Services for Dreisilker Electric Motors. Howard, welcome.
Thank you, Jim. I'm here today and we're going to discuss electrical motor diagnostics. It's a very important topic as electric motors are the prime mover of industry today. And in the past, most technicians have been fixed with just multimeters and, if they're lucky, insulation resistance testing. So what we'll do today is we're going to cover a little bit on the electric motor, the components, and then how some of that testing is performed. In this case, this cutaway of an electric motor. Inside the electric motor, we'll have the stator. The stator holds the motor windings. The motor windings are basically what energize the electric machine. Underneath here will be a rotor, and then we have bearings that hold it centered within end shields. The end shields hold everything centered. And we want this rotor to be within this motor as concentric as possible, so there's an even air gap all the way around. An electric motor is a very precise piece of equipment, and the idea is that as long as everything is concentric and even and smooth, it'll operate just fine. Now, the key components that usually fail in electric machines will be the bearings, primarily, and in much larger machines you might see the rotor bars fail. But what we're going to concentrate on is the insulation system, the windings. Now, windings in all the failures fail about 35% of all motor failures, and within that, about 15% of that 35% will actually ever go to ground, including through the motor fault. So when a technician will go and troubleshoot an electric motor, they get very, very lucky if they are able to determine immediately that they have an electric motor problem. The result will often be that they'll swap a motor out, swap a drive out, move other things around, and so on. So the winding itself looks like this. This is a concentric winding, which means I have an inner coil going from here to here, a middle coil, and an outer coil like this. The other type is called a lap winding, in which they're all evenly all the way around, like a cornucopia. This part of the system will have certain insulation components, which include the tying tape, which holds everything down, the enamel on the wire, and then your slot liners and slot sticks. The slot liners on most machines nowadays are a Class H Nomex insulation system, which is very, very firm and capable, but it's also very smooth. And the reason it's smooth is this acts as a lubricant for the wire to expand and contract. So whenever this machine starts, the windings want to pull themselves into the motor, moves in the slot, and so on. That material basically looks like this, and then it has to be formed. The material that holds down the winding is called a top stick. and that's usually made out of Nomex as well, just a very thick material. And that goes down into the top of the slot and holds the winding in place. These are very important components. And then finally, the last piece will be the phase paper. This phase paper goes in between the coils to keep the phases from shorting together. All of this is meant to also hold the insulation system material firmly in place, mechanical strength. Now, the insulation system, or the coils, are made up of different materials as well. On my low voltage machines, or your under 600 volt machines, this material is your wire. The wire will be usually copper, sometimes aluminum, and it'll have an enamel coating on it. The enamel coating is your actual insulation system for the electric motor. It acts like a pipe, and then the copper wire acts like the center of the pipe where your electricity or your water would flow. In a random wound machine like the one that I was just showing, we'd have this type of coil. In my larger machines, or medium voltage, 2300 and 4160, I'll have a coil that looks something like this. This coil is formed, and then it's placed in the slot of the motor, and then the top is connected from coil to coil to create my winding. That material is copper as well, but then that copper has a wrapping around it. That's the rest of my insulation system. This is usually referred to as an armor tape. Okay, and all of that is there to, again, get the electricity to flow in a certain direction, hopefully not to ground. In the past, we've had limited technologies for testing this material. The most common is called a multimeter. The multimeter, I can do voltage, current, but also ohms, and the ohms are primarily what people use. The challenge with that is my AC machines actually have other components than just the DC circuit. And if I take just my standard DC resistance, basically what happens is when I have a problem with the insulation system, as the temperature goes up in that insulation system, its simple resistance decreases. So the motor will be running and it'll have a defect in the insulation system, and it'll get hotter and hotter and hotter until across that point I get a short. Now my low voltage machines, my 480 volt, 230 volt, 380 or 50 hertz machines overseas, when I run into that problem and the temperature of that fault gets to a certain point, I see a direct short. When I see that direct short, my motor trips. By the time I get to the motor with the multimeter, the insulation system is cooled down just enough that I can't see it with DC resistance. It looks like a straight coil again. The other method that's used is called a Megger, or insulation resistance tester. There's a multiple of different types. This particular one is a handheld unit, and this handheld unit basically has a test capability and can do insulation resistance at 500 and 1000 volts. This one will also demonstrate, will also take an ohm reading. Now these are our standard technologies. Now as time has moved on, there are a number of different manufacturers, All-Test, PDMA, Baker, Empath, or Framatome, Arriva, that all have different technologies meant for detecting problems with electric machines. The ones that we're going to show today include the All-Test 4, which is called motor circuit analysis. That's a de-energized test. Now, we're going to show you at the motor, although this testing can be done from the motor control center or disconnect. And then for online testing, I'm just going to show you the readings from an online tester. In this case, this is the All-Test Pro online unit. Baker, PDMA, and Arriva also have similar test equipment for taking a look at the electrical system while something is live. It's called motor current signature analysis or electrical signature analysis. The difference between those is that my motor circuit analysis test equipment is going to tell me what's going on in my insulation system between conductors, in the air gap, in the rotor of the machine. It's going to tell me if I have turn shorts occurring or other insulation problems that I will not see with an insulation resistance test. The online unit is going to tell me real time what's going on with the motor, the supply voltage, the supply current, and then in the machine what's going on in the air gap, the rotor, if I have coil movement, and then also the driven load and other systems, other parts of the system. That is hooked up using voltage clips as well as current clamps. Okay, so we'll start out by doing a simple resistance test and a simple insulation resistance test. In this case, we have a simple machine here of about 30 horsepower, and this machine we're going to do a DC resistance test. Here the instrument's set up to show me resistance, and I'm going to do the typical testing. The typical testing is, say, from A to B. Okay, so in this case I have 0.39 ohms, 0.39 ohms, A to C. In this case I have 0.42 ohms, or 0.4, and then B to C. And in this case I have about the same, about 0.4 ohms. This will not tell me if I have an issue with the machine other than if I have an open winding or a loose connection. Now that I've done that, I know I have continuity in this case, but now I can perform what's called an insulation resistance test. And that's using the Megger. Now in this case with the Megger, I can also do something called a polarization index or dielectric absorption test. Both cases, what that does is it gives me a ratio of the insulation resistance. What I'm literally measuring is the current flow from the windings across the insulation barrier to ground. So if I hook this up to the ground in this machine, to the ground in this machine, I can now test to see how this is, what condition it's in. Now a standard megohm test is performed for 1 minute, and when it's performed at 1 minute, you then have to adjust for temperature. And here it's about 30 degrees centigrade today, so my insulation resistance test is going to be roughly half of whatever I read. So when I come across, I'm at 500 volts, and I will hit test. I'll hold it here, and I go straight to infinite or 550 megohms for this particular device. That means I don't have to test that part anymore. But if I go to 1,000 volts, once I start up, I will get into an area called the gigohms, and if I go into hundreds of thousands of megohms or thousands of gigohms, that's called a teraohm. So as I hold this, I look here and I'm at 2.6 gigohms. At this point, I can still perform a polarization index or dielectric absorption test. And what I'm looking for is a polarization index greater than 2.0, or if I have 1,000 megohms, I'm expected to see 500 megohms when I start, 1,000 megohms later, or a dielectric absorption of 1.4. That's the 1 minute test to the 30 second test, and a PI is my 10 minute to 1 minute ratio. The other thing I want to watch for, and most people don't realize this with insulation resistance testing, I can tell if I have a damp winding or a lot of contamination in the winding or a dried out insulation system if while I'm doing the test it climbs, decreases, climbs again and decreases and so on, because what I'm having is capacitive discharge. And capacitive discharge occurs when I do have a short that, you know, it builds up to a threshold and discharges, builds up to a threshold and discharges, and so on. If I see that, then I have an insulation problem. Now those will tell me what's going on as far as continuity, and so far as my insulation to ground, or literally the barrier between the conductors and the ground wall of the machine itself. So now what I want to look at instead is what's going on between the conductors. Now each of the offline or motor circuit analysis devices have different strengths and weaknesses. PDMA focuses on insulation resistance testing and inductance testing. So it looks at the air gap, the rotor, and then takes different views of the insulation to ground condition. It also detects issues that are heading towards severe shorts, and also will detect continuity issues, loose connections, through a 4-wire Kelvin bridge. The all-test instrument, on the other hand, what it will do is it takes readings of resistance, the capacitive impedance of the circuit, meaning what's going on between conductors. So I see the AC resistance of the circuit, my inductance, which is the potential magnetism of the coils. That will also tell me what's going on with the rotor. A special test owned by All-Test called the phase angle test, which is the phase angle of the insulation resistance. Another one called current frequency response. What it really comes down to is what you need to know is if impedance and inductance follow the same pattern, it's good. And if the phase angle and current frequency are plus or minus 1 digit of each other, that's also good. So what we'll do is we'll perform this test and see what the condition of this particular machine is. First thing it does is you have to zero this out. And then we're going to connect it, and I'll bring this close to the camera as it tests. So I press OK, and I let it run through its readings. Okay, and that's the first phase. I'll press OK, and it asks me now to connect to my second winding, so I'll go A to C. And I press OK, and it's going to run through that same set of windings, or same set of readings. Okay, and that's my second phase. I press OK again, and I'll move this here, and I'll say OK again. And this test runs about 20 to 30 seconds total. It will also do an insulation resistance test within certain limits. I tend to carry a separate megger with me, so I'm going to skip the insulation resistance test because we've already performed it. And here are my final results. Across the top I have resistance, in this case 0.255, 0.270, 0.247. Now, difference between this and a Kelvin bridge is called a 2-wire Kelvin bridge, but it also puts out a pulsed output. So if I have any loose connections at all, it shows up. The next one that says Z, 75, 83, 84, that's my low, medium, and high reading. I scroll down to my inductance, and here I should see a low, medium, and high, or 14, 16, and 16. That means that any unbalance I'm seeing is a result of the rotor position. Now, while I'm down here, minus 43, minus 42, minus 42, those are that current frequency response. Those are within a plus or minus 1 of each other, so that means I don't have any winding shorts. And if I scroll back up, 78, 78, 78, that's the phase angle, again, all within plus or minus 1, meaning, again, I don't have a winding short. So if both of those are bad, I've got a turn-to-turn short. If the phase angle is good, but that current frequency is bad, that's a coil-to-coil short. And if my phase angle if my phase angle is good and my current frequency is bad, that's a phase-to-phase short. If the current frequency is good but the phase angle is bad, then that's going to be a coil-to-coil short. So you can get some detail with it. It's not a bad device, and I've used it in lengths, in excess of 1,000 feet. Now that covers the basic instrumentation, and as you can see, there's a lot more flexibility than there was in the past. Now I do have a screen up showing what the online testing is capable of doing. On here, this is actually from an electric motor. The call was noise, and when we went out there to take a look at it, you can see the top screen here is RMS current. That's the actual current the motor's seeing across 60 seconds. This is and what's called a fast Fourier transform of my current across 120 hertz, and this bottom one is called demodulated current. This is not worth that much. This is where I'm looking, these two parts here. When you see this peak, high peak, then a low peak, high peak, and a low peak, when I look at a pattern like this, it actually turns out that this motor was hooked up to a gearbox that is a typical gearbox failure. So through the air gap of the electric motor, through just looking at the current analysis of the machine, we identified that the electric motor wasn't the problem, but the problem actually lay within the gearbox or the driven equipment itself. This one here, you see the center peak here, that's actually my line frequency, and all of your current signatures are amplitude modulated. And what that means is I'm going to have sidebands of everything. So if I look from here and I look on either side, all of these peaks here and all of these peaks here actually relate to the different gears within the gearbox and the problem with the gears within the gearbox. In this case, a lot of backlash and hunting tooth frequencies. So as you can see, technology has gotten very, very flexible nowadays, to the point where the electrician or the troubleshooting person is not limited anymore to just the multimeter and the megger. And what's very important about all of these technologies we've covered is that they're flexible for virtually any type of application. For systems over 600 volts, you would go in with live testing. You have to use current transformers, the CTs, and the potential transformers, or PTs, to collect your data, because none of the manufacturers make anything over 600 volt capable. The low voltage tests, as well as some of the newer higher voltage tests, such as the advanced winding analyzer, which is the SKF Baker equipment, can be used from the motor control center or disconnect to be able to detect the condition of your machine at a distance, which is phenomenal as far as troubleshooting. It takes things that used to take us hours in the field and brings them down to minutes, basically, in order to detect a problem. I'd say the biggest thing we run into is the confidence in believing what the technologies tell you, and still the experience of using the human senses, because nothing beats a sense of smell and then the look of the piece of equipment and the condition of the windings. So I think we've covered quite a bit in a very short period of time, so I'm going to toss this back to you, Jim.
Well, thanks, Howard, for that interesting presentation. And before we let you go, we do have a few questions from our attendees. The first one asks, can EMD technologies predict equipment failure?
Absolutely. In particular, not just predict the failures, but give you an estimate of how much time you have left for the equipment being tested. So, for instance, if I detect some damage to a bearing, and I've tested for a period of time, and now I'm detecting that the bearing is beginning to wear out, I can apply very specific and very simple reliability rules to determine what the percentage chance that I will survive 1 week, 2 weeks, and so on. For those of you that are in the reliability industry, that would be basically using the reliability formula, the natural log of the amount of time times the failure rate of the machine. And that will give you a percentage chance that the machine will survive that length of time.
All right, and this next one would like to know what their strengths and limitations are.
Well, that is another excellent question. All of the technologies have different strengths and limitations. For instance, your ohm meter will only detect if I have a loose connection or broken conductor. My low voltage motor circuit analysis will detect degradation of the insulation system, but not necessarily gaps in the insulation system. The higher voltage testing, say PD surge or surge testing, is going to tell me when I have a weakness in the insulation, but not necessarily that that it is aged. And then my motor diagnostics testing, such as electrical signature analysis, are going to detect certain things, but in particular may not detect bearing failure as far in advance as, say, vibration analysis. So what it really comes down to is making sure you've selected the right technologies that fit their capability. For instance, a Megger test is not going to tell me that I have a turn-to-turn short. It's just the limitation of the technology. So if I know that I'm going to be looking for turn-to-turn shorts, I'm going to select or want to select the technologies that will help me detect that problem.
And with that, Howard, we're going to have to wind things up. I want to thank you for taking the time to answer questions from our attendees and helping us all understand a little bit better.
Thank you very much, and back to you, Jim.
Well, today has been a day packed with valuable information. We learned about the highly dynamic capabilities of nanopositioning. We took a look at primary error sources in precision mechanics for linear motion applications, and we learned what to expect from a distributor and systems integrator, as well as learning how to use EMD for time to failure estimation. At this point, I encourage your participation on the exhibit hall floor, where you'll find key manufacturer exhibit booths manned by manufacturer product representatives, engineers, technical specialists, and other professionals from these organizations. They have a good deal of valuable information to share with you, such as new product releases, technology applications, video demonstrations, and a variety of materials. Remember, anything you may have missed from today's event can be viewed again via our online demand service. But the exhibitors are only here today, so spend some time with them while you can. Please take advantage of all of these opportunities, and don't forget to visit us right here at www.globalspec.com/events to learn more about upcoming online events that you won't want to miss. I'm Jim Brennan. Thanks for being with us today, and we'll look forward to seeing you again at another GlobalSpec e-event.